Hello, this is lesson 1 for chapter 16. Here we'll be talking about electrical forces and fields, and I'm giving you a little preview of the chapter here. We're going to learn about the behavior of atoms. Guess what? It didn't go away last year when you finished chemistry. We're going to start talking about atoms again, but just a little from a different perspective here. So when I ask you what charges of certain things are, you should still remember those things because you did indeed learn them. We're going to talk about the history of electricity. We're going to talk about forces between charged particles. We're going to talk about electrical fields. And why will I allow myself to be shocked many times in the name of science? And I stress the word many, especially since we have a new Van de Graaff generator. Well, the first thing we need to talk about is simply charge. And here we have to take a historical perspective. Good old Ben Franklin. He named one charge positive and the other one negative. And when you really think about it, does that name matter? No, it doesn't matter at all. He could have called what we now know are electrons positive and what we know as protons today. He could have called those negative, and it would make no difference whatsoever. It would simply be changing a name of things. The big idea there is that they are two charges. And the way they behave is what is so important to the whole idea. For example, opposites attract. You know this. A negative charge will attract to a positive charge. Like charges repel. So two negatives, or in fact two positives, would repel from one another. Time for an example that may or may not have happened in real life. Bob scoots his feet in woolly socks across the floor. What will happen when Bob touches his sister's ear? Well, as you can see from the illustration, Bob has built up a negative charge by stealing electrons from the carpet. So as Bob, let me grab a hold of Bob, as Bob scoots across the carpet, you guessed it, there's a shock. Now, what a shock is when we talk about static electricity, because that's what we're talking about here, a shock is simply a transfer of electrons. Now, if it's big enough for us to see it, it's a fairly decent sized transfer of electrons. Now, the thing about that is those electrons aren't just going to hang out on our ear. They're going to do something else. They're going to go towards the ground. That's what we call grounding. That's what grounding is. So if you're reading something or you get a question about what is grounding, grounding is where the electrons go to the ground, because you see the Earth is a giant it's a giant bin for holding electrons. And the reason I say it that way is in nature seeks equilibrium. Well, when Bob's alone over here, he is not in equilibrium. Nature seeks to get back to the equilibrium. So those built up electrons jump to his sister's ear because that's a convenient place to get out. They will then transfer from her ear down through her body, through the chair, to the ground to neutralize the scenario. And that's the big idea. Nature always wants to neutralize things. This winter's been a terrible example, and I'm appreciating it very much. But normally in the winter, getting out of our car, I get shocked. And perhaps you also experience this. This is because as in dry winter air, in your home you may notice this with lots of static electricity. Dry winter air traps electricity places, traps the static. It can't get out easily. You'll notice in August, August and July, very humid months around here, you don't have this problem. But usually in the winter, in the dead of the winter, like right now, I will get zapped every time I get out of the car. It's very frustrating. That's because my car is not well grounded. It's insulated, as a matter of fact, and all the static electricity charge that builds up on my car as we drive around doesn't get out until I open the door, step out, and touch the door and the ground, and bam, I am a pathway for the electrons to neutralize themselves and get back to a state of equilibrium. Used to be, back in the day, old trucks, especially fuel trucks, would actually drag a chain behind, a small chain, not a huge chain, but a small chain behind them as they drove down the road. So that as this big truck, especially a fuel truck, was driving down the road, if it built up a static electric charge, it would be discharging it, because that metal allows the electrons to flow outward and get back to the world and not have a buildup. Because you can see the potential danger. If you would have a static discharge on a fuel truck, there could be a very unfortunate problem. Well, let's talk a little more history here. There was this guy back in 1909, and no, you don't have to know what date that is. His name is Robert Millikan. He discovered that electric charge could be quantized, meaning he gave it a number. He said that plus or minus 1 electron means, or plus or minus 1 E means plus or minus the charge of an electron. And so if you see something 2E, that means the charge of 2 electrons. Or positive 2E, it would be essentially the charge of 2 protons. How did he do it? And here's the big thing. How he did it was, let me click to the online textbook. Textbook, I don't care about Gradebook Wizard. Textbook, please, thank you. What he had was this neat little setup. This is an atomizer. Oh, darn thing. That's an atomizer. And atomizer is an old-fashioned perfume sprayer. And he had this setup here where he had these charged plates and a charge plate. And what he could do is, see that oil drop? I gotta move the mouse around, but see that little drop right there? By changing the charge on this plate and then on this plate and this plate and this plate and this plate and this plate. See how I say ask your teacher to explain it? Yeah, I'm trying. Get your finger out of the way. As he switched the charge back and forth on the plates, back and forth, he was able to make that oil drop dance back and forth and actually use charge to manipulate the oil drop. It's actually kind of neat. Well, this experiment led him to, and let's go back to the notes, led him to come up with some ideas. He found that 1 electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. That is our new unit. We will learn about Mr. Coulomb a little later. 1 electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. He also found that if you have an object with a negative 1 coulomb charge, it contains a whole mess of electrons. 6.2 times 10 to the 18th extra electrons. So if you gather 1 coulomb of charge, you are gathering 6.2 times 10 to the 18th electrons. That's a lot of electrons. Of course, positive things work the exact same way. It's just that they lost electrons instead of gaining them. Quick little practice for you to do in your notes. What is the charge of 7 electrons, and how many electrons in a negative 7 coulomb charge? Figure that out. Go ahead, pause your recording so you can figure it out. Then I'm going to show you in 3, 2, pause it, 3, 2, 1. Okay, what you do is charge of 7 electrons. Well, you have 7 electrons, and this is the charge of 1 of them, so you're going to multiply by the charge of 1 electron. How many electrons are in this charge? Well, there's this many electrons in 1 coulomb, so again, you would multiply by that number. Alright, that's going to be on tests and things. Learn it, know it, remember it. Another practice. This balloon has a charge of negative 3 coulombs. How many extra electrons are built up upon its surface? As you can see from the illustration, there's a bunch of electrons built up upon the surface of the balloon. Figure it out. Pause it. Pause the recording. Do it. Okay, you paused it. Good. You'll find 1 electron. It's a tiny little electron with a tiny little charge. But 1 coulomb is big. It's a big charge, has many electrons. So that means you needed to multiply your 3 coulombs times this number. I hope you're getting this. Hope you're getting that. Talk about insulators and conductors. An insulator, what is it? It is a material that does not transfer charge easily. I said easily. Insulators are very good at gathering charges on their surface at times, but they don't want to travel through it. Whereas a conductor, the material does transfer easily through it. Examples of both. A conductor example, a classic example of conductor is metal, but water also works. And there's some other ones, but I mean, we're going to talk about metals or water most of the time. Insulators, a lot of things. Wood, plastic, fur, glass, silk, wool, cloths. Most of your cloths, plastic is one of the big things that we talk about when we talk about insulators. Now we can talk about, we saw earlier how we can charge an object by contact, but here we're going to do another way. It's called induction. What we're going to do, number one, you bring a charged rod, that's this red thing, that is charged negatively, toward a metal conducting sphere. That's this. There's also a diagram in the book. You bring it near. You don't touch it. What happens is the negatives in the sphere run away from the negatives in the rod. Well, the next step is you ground that metal sphere. This causes this gives the electrons a chance to escape farther, so they run away. You pull away your conducting wire, all you got left is the negative or the positives, and you pull away your rod and you're left with just a positive sphere. Now, this is an overly simplified drawing. Is every single electron gone? Of course not. But a significant number of electrons did run away. Induction. Learn it. And lastly, in addition to charging things through induction and contact, we also have polarization. Polarization is where the atoms on the surface spin around because they're attracted to or repelled by another charge. The charges don't go anywhere, but they just spin around. I want you to visualize, and I'll probably do this in class for you. Taking a balloon, inflating a balloon, rubbing it on a sweater would be something someone would normally do this on. I probably won't be wearing a sweater. But you rub it on the sweater and you stick it to the wall. The charges there in the wall didn't go anywhere. The balloon was charged through contact with the sweater, but the wall didn't change charges. What happened was the atoms in the wall simply pivoted around so that the balloon could cling to it. Okay, and you'll see down here there's a video that we will watch in class. And what is this little lightning bolt going to tell you? 553, 1 through 6. Enjoy.